This is your phone. This is your grandma's camera. These are your headphones. Now the amazing thing is, all of these are powered by the same stuff. Now what is that stuff, you might ask? Well, stick around to find out.
Siji the science guy. Siji the science guy. Siji the science guy.
Science rules.
Siji the science guy.
Inertia is a property of matter.
Siji the science guy. Siji the science guy.
Brought to you by electrons, making your world a brighter place.
You ever wonder what keeps your phone on? Your computer? And this? They're batteries. Batteries! But there's so many different kinds, like regular AA batteries, lead acid batteries in your car, and lithium-ion batteries. Considering the prevalent use of lithium-ion cobalt batteries in phones and electric cars, how do they work in comparison to traditional battery technology, and what makes them more effective? You may wonder now, why are there so many different kinds of batteries? Well, each kind serves a different purpose. And you know what? We should be in the lab.
The what?
Have you seen the lab? Oh, here it is. Aha, my hot dog is ready. Lithium-ion batteries are much like hot dogs. No kidding. In a hot dog, there's a piece of meat with two buns around it. In a lithium-ion battery, there's the cathode, the anode, and in between is a separator that allows electrons, electrolytes, and different ions to move around. In a hot dog, there are also some goofy chemicals called mustard and ketchup. When you put a hot dog in a flashlight, it's not gonna turn on. Duh. But a battery has the necessary chemicals to make electricity from the flow of electrons from the anode to the cathode. Batteries are a good source of energy. So are hot dogs.
You screwed up.
Got it. This is a lithium-ion battery, which is a redox reaction. The oxidation reaction takes place at the anode. Here you can see LiC6 gets oxidized or loses electrons and turns into C6 Li plus ions and gives an electron. The reduction reaction takes place at the cathode, where you can see that the COO2 gets reduced and bonds with the Li plus and the electron to form LiCOO2. Now when you add up the oxidation and reduction reactions, they form the overall reaction of the lithium-ion battery, where you can see that the LiC6 and the COO2 combine to form C6 and LiCOO2 with the E cell of positive 3.6 volts. This means that the reaction will likely occur in the forward direction because the E cell is positive. In comparison to a lead acid cell, they are 3 times lighter and 6 times less volume, all the while holding more voltage. This is a structure of lithium cobalt oxide. The blue atoms in the center are cobalt, which have a 3+ oxidation state. Each cobalt atom has one double bond with an oxygen atom and one single bond with an O- ion. The cobalt, oxygen, and lithium in each layer are arranged in a triangular lattice crystal structure. The purple detached spheres are Li plus ions. A simplified 3D structure is shown right here. In most batteries, such as a lead-acid battery, there's a salt bridge that relieves charge buildup in the cell. But to prevent leakage and reduce size, lithium-ion batteries use a separator that serves the same purpose. Typically in galvanic cells, 2 common salt bridges are KNO3 and NaCl. The salt bridges sit right in between the anode and cathode, acting as a mechanism to relieve charge buildup in each electrode. Both KNO3 and NaCl are ionic compounds, meaning their atoms are held together by ionic bonds. As ionic compounds, they make for good salt bridges because when broken into their respective ions, each ion possesses either a +1 or -1 charge. This allows them to effectively counteract charge buildup in the electrodes and prevent the battery cell from rapidly reaching equilibrium or dying. For example, the flow of NO3- ions into the anode would effectively balance out the positive charge from the cations released during oxidation. Here is the 3D structure of potassium nitrate. The blue spheres in the center are N+ ions, which each have a double bond with an oxygen atom and 2 single bonds with O- ions. The purple spheres are K+ ions. Potassium nitrate takes the form of an orthorhombic crystal structure at room temperature, but it becomes a trigonal crystal structure at 129 degrees Celsius. Here is the 3D structure of sodium chloride. The alternating green and purple spheres are Na+ and Cl- ions. They are arranged in a cubic crystal lattice structure.
Oh, sorry, didn't see you there. What's this, you ask? Well, I'm just calculating the voltages for lithium-ion batteries and alkaline batteries. You see, voltage is a measurement of how hard the electrical circuits are pushing the electrons to power something. For a traditional alkaline battery, it can only produce 1.43 volts, whereas a more powerful lithium-ion battery can produce a voltage of 3.6. This translates to greater capacity for work, which is equivalent to more power. The Gibbs free energy, or delta G, is something crucial to look at when comparing different batteries. Based on the voltages of the batteries, we can figure out how spontaneous their chemical reactions are, and whichever one is capable of doing more work. Using this equation, we found out that the delta G for an alkaline battery is negative 275.95 kilojoules per mole, whereas for a lithium-ion battery, negative 347.95 kilojoules per mole. From this, and assuming, of course, similar rates of electron transfers, we know that it would take longer for a lithium-ion battery to reach a delta G of 0, meaning it'll run longer than alkaline batteries. So, why do batteries die?
Well, let's imagine this baby whale here as the QC, or the initial concentrations of the products over reactants. It is very small, meaning the battery consists of mostly reactants, resulting in the electrons having the highest likelihood of transferring spontaneously. As the redox reaction occurs and the reactants are converted to products, the QC approaches the KC, or the mama whale, which is incredibly large, as it consists of nearly only products. When QC equals KC, this means that the battery has reached equilibrium, which results in the battery dying as there is no tendency for the forward reaction to occur faster than the backward reaction. In the case of an alkaline battery, once it dies, it is dead forever. However, a lithium-ion battery can be recharged. When you charge a lithium-ion battery, the influx of electricity forces electrons to flow in the opposite direction, turning the products back into reactants by causing the originally reduced chemical to now oxidize, and vice versa. If you think of the inputted energy as a product of the reaction, charging the battery causes the products to increase. So, due to Lichat's principle, the excess products will cause the reaction to shift backwards.
During the transfer of electrons in a battery, ionization energy is required to determine how much energy is required to give up electrons in oxidation. Lower ionization energies result in better reducing agents, as they're more likely to give up their electrons. I've got a joke for you. What did one charged atom say to the other? I've got my eye on you.
I got my eyes on you.
So, why is this important? Lithium in lithium-ion batteries has a lower ionization energy than the zinc in alkaline batteries. To get a better understanding of this, let's look at the periodic table. Lithium is closer to the bottom left corner, which means it is overall a larger atom. Being a larger atom, it has better electron shielding due to there being more inner shell electrons. Since the negative charges of these electrons repel the outermost valence electrons, lithium is more likely to lose its valence electrons than zinc. Therefore, lithium is a better reducing agent, and the lithium-ion battery has a higher cell potential than alkaline batteries. In short, lithium batteries are more likely to lose their electrons, which will cause them to work. So, let's set up a demonstration to better understand this. The ion here will first act as a zinc ion in an alkaline battery, and the ball can be an electron. when he tries to give me that bulb, it won't be as strong, which represents the zinc not being a very good producing agent. However, let's say examples of lithium-ion battery. Since lithium is a much stronger producing agent, when he throws me the ball, it will be much stronger and be more willing to give up that electron.
Ouch.
So what this shows is that lithium is a much stronger producing agent, and therefore has a higher cell potential, and overall lithium-ion batteries are just more likely to work. A great way to compare batteries is to calculate the coulombs of charge they produce. Let's start with a 1.5 volt AA alkaline battery. This battery contains 2,500 milliamp hours, and if we multiply this by 60 minutes over 1 hour, then once again by 60 seconds over 1 minute, we get that this battery produces 9.0 times 10 to the 6th milliamp seconds. If we take this 9.0 times 10 to the 6th milliamp seconds and divide it by 1,000, we get that there are 9,000 amp seconds, which is equivalent to 9,000 coulombs of charge. We know that amps are equivalent to coulombs over seconds, so if we divide the 9,000 coulombs by 3,600 seconds, which is equivalent to 1 hour, we get that the AA alkaline battery produces 2.5 amps. Let's try the same calculations with the 1.5 volt lithium-ion battery. This battery contains 1,600 milliamp hours, and if we multiply this by 60 minutes over 1 hour, and then once again by 60 seconds over 1 minute, we'll get that it produces 5.76 times 10 to the 6th milliamp seconds. If we take the 5.76 times 10 to the 6th milliamp seconds and divide it by 1,000, we'll get that it produces 5,760 amp seconds, which is equivalent to 5,760 coulombs. Since we know that amps is equivalent to coulombs over seconds, we can take the 5,760 coulombs and divide it by 3,600 seconds, 1 hour, and we get that the lithium-ion battery produces 1.6 amps. According to these calculations, alkaline batteries can produce double the coulombs of charge than lithium batteries can. The payoff, however, is that while a lithium battery may not produce the amount of coulombs that an alkaline battery does, a lithium battery can be recharged hundreds of times, therefore removing the process of having to constantly replace the battery itself. However, if you calculate the amps over 1 hour of usage, the alkaline battery can produce over 1.5 times more energy than the lithium battery. Why don't we look at a modern day comparison between the two? The 100 kilowatt hour batteries in a Tesla Model S are able to power the car for 300 miles. A AA alkaline battery, on the other hand, only lasts for about 3 watt hours. Therefore, to make that same 300-mile trip will cost about 33,300 AA batteries. Additionally, you would then have to change and discard the used AA batteries, as they cannot be recharged like the lithium cells. This proves that although alkaline batteries can produce more energy, in some instances a lithium-ion battery is simply more plausible to use.
So now that we've done all of these math calculations, what does any of it actually mean? Well, we've learned that lithium-ion batteries are lighter and can be recharged, unlike alkaline batteries. Due to their lighter composite, they are much more practical for devices such as phones and laptops. But if you want stronger energy, alkaline works like a charm. Well, that's the end of our show. We'll see you next time on Siji, the Science Guy. Now the amazing thing is, all of the
science guy.
Oh, these are powered by the same stuff.
when you put a hot dog in a flashlight like this, what keeps your phone on, your computer, and this, their battery.
Siji, the science guy.
This whole time, I've been like raising my voice like 2 octaves, and then out of a sudden I pitch it down like 4.